Hello everyone, my name is Balpreet Singh and today we're going to perform decision tree classification in R. And obviously for prerequisite you need to have R Studio installed that I've already done. You need to have some data set on which you'll be working. Let me open mine. So before I jump into what this data set is, what it's all about, first of all, what is classification? So to put it simply, you want to classify objects into different buckets, right? So let's say in academics, you want to say those who scored more than 80, they go into the toppers. Those who scored between 50 to 80, they go into the average students, and those who scored less than 50, let's put them into below average. So we create three categories and we place student in each of the categories based on their marks, right? That's what we do. Based on certain parameters, we place people or objects or things into certain buckets, known buckets, and that is why this is referred to as supervised learning. So when we create a decision tree based or any different technique or algorithm based classifier, what we're trying to do is we have some known samples, and then what we do is based on that we train our classifier that okay, if a particular instance has these attributes, we'll place it into this bucket. This is known to us. When a classifier is trained, then we want to predict the same for unknown samples, that okay, if a particular instance or let's say a student has these attributes, which is the bucket in which we want to place him or her. That's what we want to achieve here. So let's look at our data set here. This dataset contains information about cesarean section results of 80 pregnant women with the most important characteristics of delivery problems in the medical field. So as you can see, we have about 80 different instances here. We have certain attributes here. You have the age followed by delivery number, right? And then you have delivery time, blood pressure, heart problem, and cesarean. So we have kind of normalized these values. Like when you say blood pressure 2, what does it actually mean? So let me explain that. When we talk about delivery time, let's say we have 0, 1 and 2, right? So 0 basically is mapped to timely, 1 is mapped to premature, and 2 is mapped to latecomer, the delivery time, okay? Then you have blood pressure, which again 0 stands for low, 1 stands for normal, and 2 stands for high. You have heart problem, where 0 is basically appropriate, that you need to account for that, and 1 is basically you don't need to account for that, you don't have a major heart problem or anything. And cesarean, 0 is basically that you were not recommended for C-section, and 1 you were recommended for C-section, okay? So we'll go through all these attributes and we'll see whether for some patient, if they show certain characteristics, whether to recommend them for C-section or not, right? And delivery number is obviously how many births you've given before this. So is it your first time, your second time, etc, etc. So let's close this up. Let's open R. Let me open a fresh script. Let me save it. Let's say it's decision tree classification. Okay, save, done. So I saved it to desktop. The very first thing that we need to do is we need to set a working directory to the desktop. First, let's see what our current working directory is. It's not desktop, so let's change it quickly. Done. Okay. We would require certain packages that would need to be installed here. Mainly two. The first one is the carrot package, which stands for classification and regression training. And if you're working in Python, then there is a similar library called sklearn. You could use that. So I should have it installed. So let me just try to load it. Okay. Oh, I spelled it wrong. Yep. So I had it installed. Now I would require another library, which is basically our part. This is basically used for using the various partitioning function that we would require here to partition our current data into training and testing set. Done. Okay, for completeness sake, let's just mention this here. You need to import certain libraries. Done. Okay. Now the very first major step is to simply import the data, right? You're working with some data, you need to import it. It's in CSV format, you would convert it into data frame. So as to work with it. So let's do that. Read.csv. We'll mention the name of the file. Caesarean ML. Okay. And then skip equals to 1, header equals to false. Because it's a CSV file, so that's a separator, right? And we are done with it. Now, why I've written skip 1 here, I basically want to skip one row, right? Why do I want to skip the first row? Because the first row contains the header, right? As you would have seen then. The first row here, age, delivery number, delivery time, blood pressure, heart problem, cesarean. This is not actually my data, right? This is just the heading. So I want to remove it, right? So let's run it. Let's see how my dataset looks like now. So this is how it looks like. You have 6 attributes. Obviously V6 is your target attribute, what you want to predict, correct? Now by default you get these column names V1, V2, V3, V4, V5, V6, which is not that intuitive to work with. So let's change them up. Let's make headers. Let's read it again. Let me just copy this. And now I'm just going to say that I only want to read the first row, which is the header, and what I want to do is I want to pick it as it is. Let's try to run it. Let's see here. So we got the headers, right? The age, delivery number, delivery time, blood pressure, heart problem, cesarean. Now let's assign them to our dataset. Column names for our data frame equals to headers. As soon as I do that, let's again view our dataset, and now you can see the default column names have changed, right? So let's do that. Now there is a precautionary measure that you can do here, but we won't be starting with it. If some problem comes ahead, then we'll do it. Because we changed the default names, sometimes what happens is further on ahead when you will be using these column names, it will still be expecting the default names. So there's another way where you can make these names syntactically valid so that your program expect these names rather than the default names. But let's see, if we get that problem, then we'll encounter it. The next thing that we want to do here is make target variable a factor. I'll explain you why we are doing it. First, let's do it. So we have our data frame, our target variable is this, and we go it like this, as dot factor, and again the same thing. Why did we do it? So as you could see, in Caesarean we have either 0 or 1. Now what happens if we do not explicitly declare it as a factor, a level, are interpreted as numeric values. So instead of classification, it would try to employ regression. So it will try to predict some value within the ballpark of 0 point something, 1 point something here and there, right? We don't want that to happen. We don't want these zeros and ones to be treated as numeric values, rather as labels, as levels. And that is why this is important, right? Now moving on, the next step, we want to slice the data. That is, we want some data for training the classifier and some other data for testing the classifier. So let's do that. Here we'll use the create data partition function. We'll supply it with our target variable, right? That this is our target variable across which we want to partition, and I want about 70% of the data to be in one part and about 30% of the data to be another part. This sounds about right. Because it's general practice, we have more data for training and then less data for testing. So let's run this. Okay. And now let's divide the data. So we have some data for training, which is the 70%, and then we have the complement of this, for testing. Invalid subscript type language. Let me fix that. Okay, now. So now we have partitioned the data, but 70% of the data randomly chosen is placed into the training set. The other 30% is placed into the testing set. Now comes data pre-processing. Okay. So why do we need to pre-process the data? Well, it's quite simple. When you get the data, it may have noise. It may have outliers. So, for example, if we take the salaries of all the employees in, let's say, an educational institute, the salary of the director would be very far from the salary of the other employees, right? Now, if we consider that while, let's say, calculating the average salaries of an employee, that deviates our results from the mean because it now pushes a little bit towards the outlier. So we need to basically counter that as well, and then your dataset could have missing values. You need to operate on that as well. So simple function to see, let's say if your dataset has missing values, is NENA. Let me just run that. My dataset doesn't have any missing values. If in case your dataset has missing values or you want to operate on outliers and anything, you could simply use some function, let's say any dot, you have any dot omit. As the suggestion says, these generic functions are useful for dealing with NAs. They'll just simply omit them, or you could try to interpolate them. So we have a function any.interp which interpolates those values, right? That is based on what is known. We try to find the unknown. In our data, we don't need it. So now let's start with training our classifier. The first thing that we're going to do is use the train control function. Let me first write it down. Okay, so what are we trying to do here? First of all, what is the use of train control? As the document says, it's to control the computational nuances of the train function. But what actually we're trying to do here is, now let me take an example. Let's say you have 10 instances, right? And 9 of those are for positive cases. One of them maps to a negative case for your target variable. So you have a class imbalance problem. Now, there's a high chance that when we want to train your classifier was only trained corresponding to those positive samples, and it was never trained corresponding to those negative samples. So now when we try to test the classifier on the negative sample, we get a bad result because it doesn't know that that category even exists, right? This is a possibility based on how you partition the data. So to counter that, what we do is here in method we have specified repeated CV, which stands for repeated cross validation. Similarly, you have bootstrap methods and other method as well. What repeated CV does it divides the data into certain sets, and it makes sure that every set is at least used once for training, right? So we are using repeated CV. 10 here indicates how many times you want to iterate this resampling process, how many times you want to do it. So basically we'll be taking 10 samples every time, and we'll be doing it for 3 times. That's what repeats stand for. So let's run this command. It runs. Now let's simply train, right? We will be creating a decision tree. We'll use the train function. First of all, we need to pass our target variable, which is obviously Caesarean. Then we need to supply our data, which is our training data. The method, our part, that was used for partitioning, right? We're going to specify certain parameters. The most important one is basically which criteria are you going to use in order to perform the splitting of nodes. For first case, we'll be using information gain, that is based on entropy, right? I'll explain that in a minute. First, let's just write the complete command. We supply the train control. Let me just see, we mentioned everything. Okay, so what we are doing here, we pass the target variable, we pass the training data, we chose the method, we listed out the parameters, that is, we'll be splitting based on information gain, which relies on entropy, that is randomness in the data. The more the entropy, the more the information gain, correct? And basically, what we want is, we prefer shorter trees over longer trees, right? That is our inductive bias when we talk about decision trees. In order to do that, we would want a node to be chosen at the top that splits the data more, right? So that is why we use information gain. We passed on the train control that we did earlier, the sampling, and then tune length is basically, it forms a grid. It will do it 10 times, and out of those it will choose the best one, right? It will train it 10 times over. So it will form a grid, it will check certain parameters, and then it will say that okay, this one is the best one. So let's try to run it. Okay, so okay, this is the problem that I think we came across earlier. I mentioned earlier, right? It says undefined column selected. So I think it's still expecting the default column, so we'll have to change that. Let's do that. Column names of the data frame. We want to explicitly say that they have been changed, so don't expect the default column names, right? And this should solve the problem. Let's run it. It did. So I just cleared the console. Let's try to run the command again, and this time it does. Let's see how our results look like. So as it says, we use by default the cart algorithm, right? The cart technique. The training sample included 57 instances. There were 5 predictors, the attribute based on which we had to map the data into 2 classes, whether we recommend the patient for C-section or not. No pre-processing was required, and cross-validation occurred over 10 folds, and this was repeated 3 times over, and the sample sizes were 51, 51, 52, and so on. Now this is interesting. We have 3 parameters here. We have CP, which stands for complexity parameter, we have accuracy, and we have kappa. And below you can see it mentions that accuracy was used to select the optimal model using the largest value, and the final value for the model was CP 0.13, and so on. So what it actually is, CP stands for complexity parameter, and it is used to control the size of the decision tree. Like I mentioned earlier, we prefer shorter trees over larger trees. That's our inductive bias, and therefore we use CP to select the optimal tree size. So we have this beforehand, we select some threshold value, and then we say if the cost of adding another variable to the decision tree from the current node is above the value of CP, then tree building does not continue. We could also say that the tree construction does not continue unless it would decrease the overall lack of fit by a factor of CP. Now, what is accuracy? How well it fits our data, right? But I prefer kappa over accuracy. Why? Kappa is basically a metric that compares observed accuracy with expected accuracy. So let's say your observed accuracy was 80%, but your expected accuracy was 75%, right? So it's not that impressive. But what if your observed accuracy was 90% and your expected accuracy was 20%? Now that's very impressive, right? So we want high value of kappa, we want high value of accuracy, we want low value of CP for our best model. Now moving on, let's copy this command again, and this time let's say we used 15 folds and we repeated the process 4 times, right? Let's do that, and we did. Let's copy the above command, and now we'll do something different. Instead of using information gain as a split criteria, let's use gain index. Let's run the command, and it does. Let's see the results that we get for gain index. Okay, a little bit different. We'll basically predict the accuracy on the testing set. So let's leave that for later. Let's plot our decision tree. Let's see how does it look. Plot the decision tree. Okay, in order to do this, we'll use the PRP function. So first, let's say for the information gain, the final model, let's choose a color. Tweak this thing up. Let's select this line. And do the same thing for our decision tree based on Guinea index. Maybe let's change the color, right? Let's see how does it look. Pretty simple, right? Now obviously we just have 80 instances, so we could expect a tree that's this much shorter, right? Based on, and out of those 80, only 50 or so were taken for training, right? Let's see how the other one looks like. Okay, pretty similar, right? So here, the decision tree that we came up with for both Guinea index and information gain came out to be same, right? Let's see the results one more time. We had 0.16 here, 0.13 here, but we got the same tree, right? Let's just verify it again. Yes, no, 0, 1. Yep, pretty much the same thing. So let's twist thing a little bit. Let's make it 11. Let's leave it at 3. Let's run it again. Let's do this. Now let's see how a Guinea index tree looks like. See, it changed. Because obviously we are performing random sampling, we are choosing different training sets and whatnot, right? So sometimes we get the same tree, sometimes we don't. So let's go with this one, since it's different, right? The next step should be pretty straightforward. We're done with construction of a tree. We've trained our classifier. We plotted. Now let's do testing. First, let's use the decision tree based on information gain. We use the predict function. We pass our decision tree, and then we pass the data, that is our testing data. Let's run this. Let's paste the same command over here, and this time let's do it for Guinea index. Let's run it. Right, so we're done. Let's check the accuracy. So here we'll use our confusion matrix function, right? We'll pass them whatever our prediction results were, followed by, we want to compare it with what? We want to compare it with our actual results. So this is our actual results. Let me just copy it. And let me just paste it over here, and this time do it for the tree based on Guinea index. Let me run these commands. Enter. Let's look at our results. So first of all, for the decision tree based on information gain, we got an accuracy of 56.52, right? Not that impressive, correct? But again, we're only dealing with 80 instances. Our data set is quite small. Then we get other values like sensitivity, specificity, prevalence, etc., etc. And then for Guinea index, we get pretty much the same accuracy. Oh, that's interesting. Okay. So if you want to go in deep, and let's say you want to see for a tuple how it is predicted, what we could do here is, let me just go into the console, and I could say, let's say I want to predict something, and D3, I'm using information gain. I'm giving him data, but this time I'll just give him one instance to test. Correct? Let me just print it up. This was the instance that was supplied to it, and let's see what our results were. So you could see that in actuality, the instance was mapped to Caesarean 1, right? We recommend it. But our prediction turned out to be 0. So this is actually false, right? This was not correct. This was a bad result. So in this way, you could eventually compare the data. And that's about the end of it. So let me just go back here, save the script, and let's do a quick revision. So we'll be dealing with these two libraries over here, right? We import the data, and this is actually not required, but just for my preference, I don't want to deal with the default column names, right? So I chose the column names which make much more sense, much more intuitive, right? Then we want to perform classification, not regression. So we made them into levels, our target variable. We created a partition where 70% of the data went into training and the rest 30% went into testing. There was no need for pre-processing in our data, but like I suggested, we could eventually if we want to deal with outliers and other things, missing values, etc. We perform random sampling, then we supply this train control to our train function. We train our function for splitting criteria based on information gain. Then we do the same thing for Gini index, and based on what data you get, you might end up with the same decision tree or a different decision tree, and then we simply plot the decision tree followed by testing, and then finally you see your results. So I could actually print the results for the entire thing like this. So for everything, these are my results 0 0 0 0 1, right? But what I did here is much more easier to read, because now this is the tuple, this was the result, and this is what I predicted. That's it. Thank you so much for listening. Have a nice day.